the whole purpose of this course, now in its 17th year, is that everybody's a bridge builder. And so the logo of the Brooklyn Bridge symbolizes the idea of building a bridge between the incredible advances in basic biological and engineering sciences on one hand, and the needs of medicine and understanding disease and health on the other. So the whole idea is we have to be able to communicate across a bridge. Well, that's fine. But today, we're going to consider the ultimate bridge. The ultimate bridge being from the farthest reach of the cosmos to the smallest molecule. And we are, of course, extremely excited and pleased to have two leaders, outstanding scientists, to share their ideas and experience with us. So fasten your seatbelts, and now the captain is going to take charge, the director of the NIH, Francis Collins.
Well, thanks, Wynn. When Wynn gave me the opportunity to do the introductions this afternoon, I couldn't resist, because I think this is one of those unique things that happens once in a while in NIH. We like to think that we're pretty good at doing unique things, but to have these two presentations back to back is probably not something that I think has ever been attempted before. And we have two spectacular presenters to take us through the brave new world of imaging from the cosmos to the molecule. I'm going to briefly introduce each of them at the beginning, and then we will get into the presentations initially from Dr. Mather and then from Dr. Lippincott-Schwartz. John Mather is senior astrophysicist in the Observational Cosmology Laboratory at NASA's Goddard Space Flight Center and a senior project scientist on the James Webb Space Telescope. But he's best known for leading NASA's Cosmic Background Explorer, or COBE, which I guess is said COBE, or it could be COBE, but COBE. Okay, the COBE mission, which was started in 1974 and launched a satellite in 1989, and on April the 23rd, 1992, announced the results from that satellite, detecting tiny variations in the cosmic background radiation, looking back at the very start of the universe at the time of the Big Bang. His book on this research, which won him the Nobel Prize in 2006, along with George Smoot, his book is called The Very First Light, the true inside story of the scientific journey back to the dawn of the universe. John's background includes undergraduate at Swarthmore, which happens to also be true of our other speaker, which is interesting. Swarthmore is doing pretty well here today. He got his PhD at UC Berkeley in physics, of course, and did a National Research Council postdoc at Goddard in New York City, but has been at NASA Goddard since 1976. And now overseeing the James Webb, or a significant part of it. This is the next big thing after the Hubble. Jennifer Lippincott-Schwartz, well known to many of you because of the long and very productive time she spent at NIH as a researcher. She's now currently senior group leader at HHMI's Janelia Research Campus, not far from here. She grew up in Kansas and then in Virginia. Her dad was a chemistry professor. She went to Swarthmore and studied psychology and philosophy, searching for some very non-chemistry thing, I guess. She went to Kenya to teach, but she taught physics, chemistry, and biology there to high school girls, and then returned, did a bit more teaching, got a perspective on what science was all about, ended up getting a PhD at Hopkins in Doug Fambro's lab in the Carnegie Institute of Embryology, and then came to NIH in 1986 as a postdoc in Rick Klausner's lab, became a staff fellow, rose to chief of the section on organelle biology in the cell biology and metabolism branch at NICHD, and did some amazing things. Her group with George Patterson especially created a photoactivatable form of GFP, which allowed them to switch a tagged version of this protein on using flashes of light. This led to a remarkable collaboration with Eric Betzig, who came and, I guess, sort of hung out in the basement or something and developed a particularly remarkable new technology called PALM, photoactivation localization microscopy, which could be used to assemble images of organelles at the molecular level. Eric Betzig went on to win the Nobel Prize in chemistry in 2014 for this work in developing super resolution microscopy, but we think Jennifer probably should have been recognized in that way as well. I'm just saying. We were very fortunate to have her in our midst as an invaluable, innovative, and indomitable NIH researcher, but we're glad she's not far away in Janelia Farms, where she's been since 2016. So with that introduction, it's time to let these two amazing scientists tell you about their research. By my calculation, the size of the universe is about 10 to the 27 meters. We're going to hear about super resolution microscopy down to the 1 nanometer level. So you're about to travel through 36 orders of magnitude. Put on your seatbelts and let's see where it takes us. Professor Mather, please.
I want to talk about some of these many orders of magnitude because when Wynn asked me to talk, I said, well, what am I going to talk about? Do you just want to talk about your own work, or how about some other people's work? So I've been interested in some of these topics for a long time, even though I'm not as expert as many of you. So the picture that I'm showing you here is a picture of the James Webb Space Telescope, and we'll get to spend a little bit of time talking about it. It's a joint project of NASA along with European and Canadian space agencies, and so basically every Earthling will get to use it in one way or another. There are about 10,000 professional astronomers, which is small compared to you all, but they will all try. We're about to receive thousands of proposals for how to use it. There are thousands of us have been working to put it together, and eventually we will launch it in a year and a half or so. So then you'll get to see, well, what did it do? So, but stepping back a little bit, I might have been a biologist. This is where I grew up. I research farm of Rutgers University in northern New Jersey. And in that barn were not only about 20 bulls who lived there and became unknowing fathers of thousands and thousands of young calves, but also research labs, chemistry and various other things. My dad was working on the genetics, and so when I was in 9th grade, I got to learn statistics, at least as needed for a biology experiment. I had 8 baby rats that lived under the kitchen table, and my mother was very patient about that. So anyway, what actually got my attention was astronomy. When I was 6, my dad told me that we're made out of cells with chromosomes, and that explains a lot, except it didn't explain much yet, because we didn't even know about the double helix yet. When I got to high school, I thought, well, biology is much harder than physics. I'm going to do physics. So it all turns out, but you never know how. So I like to talk a little bit about why are these things interesting. And so the big question that's, I think, in a lot of people's minds is, well, okay, we're here. How did that happen? We might believe in atoms, so we've been hearing about atoms for a long time. But how do the atoms turn up to be us? And be able to write something like what Jefferson wrote in our Declaration of Independence, that all men are created equal, that they're endowed by their creator with certain unalienable rights. Among these are life, liberty, and the pursuit of happiness. So none of those things are written in the laws of atoms that we know of yet, but somehow it happened. So sort of summary on one page of 6 enormously difficult challenges. Quantum mechanics, we have known about it since the 1920s. It tells us how matter behaves. And if you could solve the equations, you would say, aha, now I know how concrete should behave because I know Schrödinger's equation. Well, no, it doesn't work. It's much too hard. So this part of physics is also too hard, so it's better to go measure. And that's true about an awful lot of stuff. We have found out since 1929 that the universe is expanding, and that it must have been very hot and very smooth when it was young, and we'll get back to that a little bit. We have found out that it's unstable in practically every fashion, that there's nothing that just sits there forever. Gravitation, for instance, was able to pull the expanding material back together to turn it into galaxies and stars and planets and people. And that's just one of many examples where people think, well, that would never happen at random, but it does because energy is released. Exothermic or thermodynamically favored at any rate, to produce complexity out of what we think of as simple. So the universe is probably infinite, which means it goes on and on and on and on. You cannot come to the end, even if you could in imagination. So we can't prove it because we don't have an infinite amount of time to go look. The universe is very old. It's about 13.8 billion years old. And so it's been plenty of time for it to try out all kinds of possibilities, even things that are apparently very unlikely. So when I was a little kid, everyone sort of knew that life was so impossibly difficult to happen that it must have required divine intervention. And so even physicists thought this because they tried to calculate it and they said, no, that would never happen. So we did not know how to do statistics about spontaneous reorganization into complex systems and phase changes. None of that was known. We have certainly learned about stored information, and we have in our cells, of course, DNA that records our instructions. But what we don't really know much about yet, and I know you're all working on this quite hard, is how does the DNA get read? How does the signal become interesting? And what does it control? So because of all this, we've got life and evolution and what I call survival of the lucky. Another thing that happened when I was little was people seemed to still believe that human beings were the pinnacle of everything, and that therefore evolution had to be directed towards us. And by the way, that means we can also do whatever we like because we're the best. So I like to think, well, we're actually lucky, because if our particular lot of ancestors had been a little bit less lucky, we wouldn't have been here. Some of the geneticists tell us our population was down to a few hundred individuals. And if that's true, then we were very lucky, or we would not be here. Maybe they'd be Neanderthals having this conversation. Who knows? Another thing I like to bring up is that we have discovered that there is homeostasis, as you all call it. In engineering, we have feedback loops, control systems, and somehow this is a big mystery. I don't know that anybody's really figured out how this one happens, but somehow not only do we have life, but we have some life that says, by the way, John Mather is the same person that he was last year and 10 years ago and almost 71 years ago. Almost all the atoms have been replaced, but I'm still me. How did that happen? So feedback loops, homeostasis, and so forth. So there's a lot of big mysteries for us to tackle all at once, and I'm not going to do it. So, but Jane, my wife here is with me. She likes Lucretius, and here's a quote from Lucretius that actually talks about some of this. No single thing abides, but all things flow. Fragment to fragment clings, the things thus grow until we know and name them. So I like this because here we have language that we recognize an individual, and by degrees they melt and are no more, the things that we know. So the poem goes on, but this is a remarkable statement. So just think about that one while we go through the stories about what we think we do know. So astronomers look back in time. We look back in time because we use light waves, and light travels at a known speed. It's pretty fast, 300,000 kilometers per second, which, however, is slow enough that you can actually hear the time travel required. When you talk on the phone and your phone signal is going up to the relay satellites, you can hear the delay that your voice has actually traveled the distance before it got back to your other end. So we can look back in time by looking at things far away, see things as they were. And how do you do this? Well, of course, you have to measure the distance to know the time. So we survey the universe, and we do it with standard methods you learned in high school, triangles and angles and surveying. And also, faint things are probably farther away than bright things. And so basically, that was the method Edwin Hubble was using back in 1929. Here he is looking through the eyepiece of the big telescope on Mount Wilson and steering to make sure you get a sharp image. And in 1929, he drew us his first graph. The little dots on the graph are galaxies. A galaxy, as you know, is 100 billion stars orbiting a common center, pulled together by gravity. And what the picture shows is the estimated distance on the horizontal direction, and they measured speed of motion away from us on the vertical direction. So picture shows a trend. The farther away, the faster. In 1929, we were forced into understanding that the universe is expanding. So this is the basic picture, and the words are more confusing than the picture. So divide the distance by the speed, you get the age of the universe. 1929. So we were forced into it. Only two people thought this was going to happen. They were both mathematicians who had used Einstein's equations to say, Einstein, you're wrong. The universe must be expanding. Einstein told them both that they were wrong. And in fact, Georges Lemaitre, who was a brilliant scholar as well as a priest, he got told, your calculations are correct, your physics is abominable. So Einstein was wrong. The universe is actually flying apart in the sense that the material is flying apart. The galaxies are going away. You'll also notice here in the lower left corner that four of those little dots are actually coming toward us, which has an interesting, means the future is interesting for us. We'll get to that. So the Big Bang, that's what we call this, because if you try to imagine running the expansion backwards in your mind, all the galaxies come crashing in, the stars crash into each other, the temperature goes up, the density goes up, and eventually you run out of imagination, and that's what we call the Big Bang, where you run out of imagination. We have lots of physicists who believe they know, back to a certain point, and then we say we still have to give up, we just don't know. We don't have a theory of quantum gravity, which we think we need. So we've invented lots of ideas, with lots more ideas than we have measurements. So that's the Big Bang and its mystery. So here's just a sort of short summary. It was very, very hot. I don't have to draw you a picture because you cannot stand outside the universe looking at it. So if somebody draws you a picture of a firecracker, it's wrong. So we think the universe has no center. Even though it looks to us like we're the center, everything's rushing away from us. You would say, well, if you lived on another galaxy, what would it look like for them? And they'd say, oh, we're the center. So the upshot is, well, we can't all be the center, so there isn't a center. It also means, since I told you, as you run your movie backwards in your mind, you run out of imagination, you cannot actually get to a first moment in this story. Just as you can't, you can divide 1 by any number except 0. So you cannot actually get to 1 divided by 0. That's not a place. So there's no, although people have talked about the moment of creation, actually what we mean here is the moment when we run out of imagination. So it's not really a big firecracker. A Big Bang is a very misleading term. And by the way, there's probably no end, but we can't tell. So cosmology, all in a very short story. So if you believe that, we should be able to tell what happens next. The expanding universe, well, it must have been very hot and very dense. We claim we know the laws of nature that should apply. We should be able to predict the distribution of the galaxies. So we actually have wonderful supercomputer simulations. I'm not going to show you the movie, even though it's beautiful, because it takes a long time. But you should be able to say, okay, computer, tell me what's the universe going to be. And then you should be able to take a picture of the sky and say, is it like that? So here's a picture taken by the Hubble Space Telescope. And what you see here in this little piece of sky, which is about 2 arc-minutes square, which is really tiny, like looking through the soda straw at the sky. There are thousands and thousands of galaxies. Each of these little specks and blobs is a galaxy. And there's one star, this one with a colored spike sticking out. And so this is a place chosen by the Hubble Space Telescope team to look where there was basically nothing to look at. And they found this wonderful surprise. The sky is filled with, well, at least 100 billion galaxies that the Hubble would be able to see, and which this is just a small piece. And they also found a big surprise. They built the Hubble telescope with an opinion and belief that they would be able to see the first galaxies forming, because we all thought, well, a lot of us thought, that it must be very slow and difficult. So the upshot of this picture is, well, no, as far as back as you can see, the galaxies were already there, or a lot of them were. So the things we're looking at, the ones that are farthest away, the ones that are farthest back in time, are their little red specks on this picture. And the ones that are big and beautiful and have shapes and colors, those are nearby. But the little red specks are the ones that have got our attention as astronomers, because we want to know, how did that happen? So after the astronomers took this picture, they pretty soon said, well, you know, that Hubble Space Telescope, it's great. It's doing beautiful things, but, you know, we still can't answer our question, what were the first galaxies like? So please build us another telescope that's bigger, better, and more powerful and can see farther back in time. So that's the one called the James Webb Space Telescope. So this particular picture was one of the most important for that. This is a picture that I put here just because it's part of our story. This is a star that blew up on July the 4th of AD 1054, which we know because Chinese astronomers wrote it down like other people did, and we still can read the Chinese records. and we think we know what their calendar meant, so we've got the day and the year and everything. It was so bright that you could see it in the daytime, and we now have the opinion that this is where most of the chemical elements of life are produced and liberated back into space. So this is a star somewhat larger than the sun in mass, and it blew up in a great cataclysmic explosion we call a supernova, and you can see the debris flying apart. Nowadays, we can point our spectrometers at it and calculate how much of every element is in that cloud. And it's not all explained. And it turned, in particular, the heavy elements, uranium, gold, and the like, are not explained in this picture. And we just got that one figured out last year. So a gravitational wave observatory was built here on Earth. It's an incredible accomplishment by our scientific friends. They built laser interferometers on the ground to be able to see these mirrors, which you can barely sort of see on this picture. This is very schematic. These mirrors are 4 kilometers apart, and the motion that they can detect is smaller than the diameter of an atomic nucleus. But what they interpreted is as a pair of neutron stars, which are old stars that burned out stars, have actually merged together, and in a great cataclysmic explosion, not only have they merged into a black hole, but some debris came flying out, and it's full of the heaviest elements. So the gold right here, it came from one of those, probably. So not only are we recycled, our atoms have been on an incredible trip. Not only are you breathing dinosaur breath, and your bones are dinosaur bones, that gold has been somewhere. So it's a pretty astonishing story to tell, and if anybody is not impressed, I'm shocked. So how did we figure it out? Well, it was many thousands of astronomers and many physicists working for many, many years to figure this out. It's not like something we just cooked up. So it's more like biology. It takes all of us to make it happen. So where do we go from there? Well, how did the solar system form? Well, we've gotten a picture lately of something that's sort of like it. This is a telescope we've built in South America. It's an international project. All these radio dishes are connected by computer, and you can simulate having an antenna that's about 10 miles across. And the upshot is you can make this little picture in the upper left corner, which is an image of an object way out there. These are dust grains that you're seeing, the glow of dust grains orbiting a new star in the middle. And the dust grains seem to have gaps in them. In these orbits, the dark areas are thought to be where new planets are being born. So a system, well, it will have about maybe 8 or 9 planets. Seems a little bit like home, although it's not exactly. But we're beginning just now to see how planetary systems like ours could be forming. So everybody wants to go have another look. It's clearly a bigger challenge for astronomers. So this is possibly how the solar system made Earth habitable. What I've got here is a simulation that shows the orbits of the 4 giant planets, Jupiter, Saturn, Uranus, and Neptune, surrounded by the debris that's left over from the formation of the solar system. The little green rocks are comets and asteroids from way outside there. And what we see here is that they orbit more or less undisturbed for hundreds of millions of years. And then gravitation takes its instability chance, and the orbits go unstable. The little green rocks go flying everywhere, and some of them brought carbon and water to Earth. That's the story. Is it right? Well, we're working on it. We'll tell you a different answer in another 10 or 20 years. But this is probably, something about this is probably true, that we were bombarded by rocks from the sky for hundreds of millions of years. And by the way, as soon as that was done, we have evidence that the Earth became alive. The fossils from the fossil evidence from about 3.8 billion years ago. And that's just about the time when this all settled down. So that's part of the answer to the question of, is life difficult to start or easy? And so we don't really know, but anyway, it was pretty quick. When it could happen, it did happen. So that's part of our story, maybe. Now here's the telescope I told you about that I'm working on. This is a project with, as I mentioned, thousands and thousands of people work on it, and 3 space agencies. We've got a big contractor called Northrop Grumman. Their big office or lab for this is in LA. So our team is often on an airplane to go visit the engineers out there. Anyway, the telescope that we see here is enormous. This golden hexagon is 6.5 meters across, about 21 feet. So it's much bigger than the rocket is, and it will have to be folded up to get it in the rocket. The big blue thing that you see here is a giant 5-layer umbrella, and it's as big as a tennis court. Also has to be folded up to go into space. And you say, isn't that pretty complicated? Yeah, it is. But we are not able to think of another way to get at the science we're after. So because we have been involved in the space program for a long time, and other government agencies also need telescopes, we can say, okay, contractors, Northrop Grumman, Lockheed Martin, can you build us a telescope? And they can say yes. So obviously, we're small compared to those other government agencies that need telescopes. Anyway, it's going up in a couple of years, roughly, in South America, because Europe is buying the rocket. And I'll show you something about what we're going to do with it. So, well, first I'm going to show you what has to happen to the telescope. We put the telescope together in our clean room at Goddard, a space flight center right over here in Greenbelt, Maryland. And after we got it together, we shook the daylights out of it to see if it would survive launch. And it did, passed that test. In a big plastic tent we had to make for it. We have to keep it clean, by the way, so it's always in a plastic tent. Then we put it in its giant mailbox, dragged it around the Capitol Beltway at night, drove the special mailbox truck into the C-5 aircraft, and flew it to Texas. I got it out again, put it in the vacuum tank in Texas, tested it as it will be in space at very low temperature, put it back in the airplane, delivered it out to California a few weeks back. Now we are in the process of making the giant umbrella work, and we'll eventually attach it to the telescope part, and then it'll look like it will look in space. And then we will fold it up again, put it in an even bigger mailbox, put it on a ship, send it through the Panama Canal to French Guiana, where we will push the button on the rocket that's being bought for us by European Space Agency. It'll go up into space, and then it'll unfold in outer space, and it'll become that again. And it'll take about 6 months before it's ready to send you a picture. So that's the process we go through. This is the most difficult project we have attempted at NASA in the astronomy program. Obviously, the Apollo program was a little harder. And by the way, the reason we're calling this telescope James Webb is because James Webb was the guy who went to Jack Kennedy with a plan. And then 8 years after the announcement, people walked on the moon. That was astonishing. Anyway, where are we going to send it? We're sending it 1 million miles away, 1.5 million kilometers. And in the picture, this is not to scale, but there's the sun, the Earth, and the moon, and the Lagrange point out here, the telescope is orbiting around that. And as usual, we don't always call things by the names of the discoverers. The Lagrange points are named after Lagrange, but Euler found the first 3. So it's not the first time things were not named after the discoverers. Anyway, we're putting it out there because it's a good place to put the telescope. It will not go farther away from Earth, and it's always overhead at midnight. We can always talk to it, and the picture is not to scale, so it's only 1 million miles away. Only 1 million miles means, though, we cannot yet go visit. Nobody's ever been 1 million miles into space. Here's our scary movie. This is what has to happen after launch. It unfolds. First, we unfold the solar panels, then the transmitter antenna and the receiver antenna. Now we begin to unfold the structure that holds up the umbrella, the sun shield. So we asked our contractors, is this the most difficult thing you ever built? And they said no. But it is right up there in the top few. We're unrolling some covers, dust covers. By the way, this is a scene you could never see really because it's dark out there. The telescope is going to be completely in the dark after we get the umbrella stretched out. Has 5 layers to keep the telescope cold. The telescope will run around a temperature of about 45 Kelvin, which is what it takes so it doesn't glow. And by the way, why would you want to make a telescope cold? We want to pick up infrared. infrared from cool objects like you. In fact, the observatory is so powerful that if you were a bumblebee hovering out there at the distance of the moon, we could see you, both reflected sunlight and the heat that you would emit. So that's what it takes, and that's what we're planning to have. So we should find something that nobody ever knew of before, that much power. There it is in the picture. It's not yet in focus yet. It will have to be focused after launch. But we figured out how to do that, and we've rehearsed that part. So what are we going to do with it? Well, we're going to take pictures. I didn't include all the pictures of the most distant universe because we don't really know what they're going to look like. And here's a picture of a place where stars have just been born. It's a beautiful, beautiful picture taken with a Hubble. And it's beautiful, but you can't see inside. Look at all that glowing dust that keeps you from seeing inside. If you take an infrared picture, even with what you can do with Hubble, you can begin to see through the cloud. The longer wavelengths of light will go around the dust grains instead of bouncing off. So you can see inside the cloud, and you can see how different it is. We'll eventually hope to see the stars being born directly inside clouds like this. We will look at places like this. If you watch enough stars long enough, once in a while a planet will go in front of a star. Maybe 1% of the stars have planets that will go in front of them like this. But we see so many that we calculate that most stars have planets. So when I was a kid, people thought the solar system must surely not only be unique, but very, very special. And there hardly must be any of them in the world, in the universe. And now we think, well, they're common, as Jane calls them, they're common as gravel. So why are we so interested? Well, of course, we're interested because we like home, and we want to know if any place out there is like home. So that's our next big challenge for these, to find some that are like home. So we already have a catalog of thousands and thousands of planets, and a few of them could be like home, but we think we're going to go look for some more, and we'll have better luck. So we will be able to do one amazing thing with this method, which is this one. When a planet goes in front of a star, some of the starlight goes through the atmosphere of the planet on its way to our telescope, and we can spread it out with a spectrometer and see what are the molecules in the atmosphere of that planet. So we calculate that for this particular star, we'd be able to see quite easily whether there's water and ammonia and methane in that particular object. So not too shabby. Now the question of Earth around a sun-like star is a much harder one, but nevertheless, we're surely going to work on it. We already have chosen a lot of targets for this sort of thing. So if you really want to know, you have to have a bigger telescope. So this one's big, but we already have plans for bigger ones, or I should say ideas. Every 10 years, the astronomers get together for a giant party, and we write a decadal survey through the National Academy of Sciences. And this sketch shows you the one that might be chosen in the lower right-hand corner. It's called the Large UV Optical Infrared Telescope. But there are 3 other wonderful competitors that also might be chosen, so we don't know which one we're going to do. They're all fabulously powerful and all fabulously difficult. And if I were to say today, I know how to do that, you would laugh at me. But eventually we can figure it out. So this is a possibility. And with one of these, you could actually see a little Earth-like planet orbiting its own star as a little dot, a little separate dot, and you wouldn't have to wait for that special chance for it to go in front of its star. What else can we do? Well, we'll look in the solar system to see what's like home elsewhere, sort of like home. So on Mars, we want to know how much like Earth is it and was it? It seems pretty likely that it was pretty wet. There's good evidence that there's subsurface ice, and we can measure better, but we're working on that. It's got various kinds of molecules. It has had volcanoes. So let's go look. So how are you going to look? Well, you can look some from a distance because we can do spectroscopy on the atmosphere. But as it happens, Mars is so darn bright, it almost can't be observed with our telescope. So we have to squint, but we've got our methods. We will be looking at places that are like this one. Titan is a satellite of Saturn. And even from our great distance, we can make a map of it with the 2 telescope. And so we'll be able to study the chemistry of its atmosphere. So I'll show you more about that. We'll also be looking at Europa coming up. Europa is a big satellite of Jupiter, which was found by Galileo himself. This picture was taken by a mission we called Galileo, and we saw this ice sheet covering an ocean, and we see these warm brown cracks, and we say, well, it's probably a little squishy there because the tides on the satellite are warming it up from the inside. Recently, we've found out that it's got geysers of warm water coming out. So with some luck, you get to eventually fly a probe through the vapor that comes out and say, well, what's in that probe? What's in that vapor? Has it got any organic chemicals in it? Even after that, well, can you land on the surface and actually pick up some of that mud or whatever that is in the brown cracks? So it's a place that could possibly be alive. Pretty unlikely to have very big complex life, but it could well have chemosynthetic life underneath. It's going to be dark under that ice, but who knows? We'll be looking at Dighton. Titan, as I mentioned, is a satellite of Saturn. It is a cold version of Earth. It has rain and lakes and rivers, but they're made out of liquid hydrocarbons. It has a pretty substantial atmosphere, about the same atmospheric pressure as we have, a little more, but it's cold. It's 94 degrees Kelvin out there. There's a fair possibility that under the surface, which has got ice, there's a liquid water under that. That would be interesting too. So there's even a possibility of little volcanoes of water and ammonia mixture coming up through the surface. So this would be a good place to look if you think, well, maybe life has got a completely different basis from what we have here because it has had billions of years to try. So if we can eventually get a sample of that, we'll have a look. We did already land a probe on this thing already, and here's a picture taken by the lander quite a few years back. So a totally amazing possibility. And eventually we could send a probe to look for signs of life. Not just big molecules, but really big molecules. We'll have to go land, though. So this is a picture I love because it shows that we don't have enough imagination. This is a picture of Pluto taken by the New Horizons probe that went by a couple of years ago. And this shows that the mountains are made of ice, and there's snow made out of solid nitrogen. Now, when I heard we were going to Pluto, I thought, well, it's just going to be another round rock like the others. But none of us had enough imagination to predict this. So I don't know that it'll have any signs of being alive, but it may also have an internal source of heat, so who knows? People now think it's got a carbonaceous core. So here's Femry's question. If we've been here for a long time, where's everybody else? So if space travel is possible, then why haven't we been discovered? So there are various possibilities. Either it's too hard, so even though we have neighbors out there, they haven't bothered, or they aren't interested in us, or maybe there isn't any. So this is one of the big questions. But we know that intelligent life has been here and with some degree of brain power for hundreds of millions of years. And people think, well, how are we going to interpret the signals we get from those distant civilizations? We don't even know how to interpret the insects yet, so wait a while, we'll get it. But in fact, we already have equipment we could use to talk and have a conversation across our entire galaxy if you had somebody on the other end who knew what you had. But we don't. So we are not yet able to have a conversation across the galaxy. So are we alone? Well, another part of the question is, well, how unusual is Earth? So this is the question, is the Earth rare or common? So right here in the solar system, Earth is pretty unusual. Not only do we have the right temperature for the surface to have an ocean, and not only do we have a near circular orbit like most of the planets, we have a very large moon. It's a quarter the size of Earth. And that seems to be important. We have a very big magnetic field. We've got a molten iron core. The magnetic field protects us from the sun. It keeps all those cosmic rays from the sun from blasting away and removing our atmosphere and making life difficult. We have just enough water to cover part of the rock. So we have oceans and continents. If we had too much water, we wouldn't be walking around. If we didn't have enough water, maybe life would never have occurred. So at least half of the water that we have is already buried in the rocks underground anyway. So if there had been a little less water, we wouldn't be here either. So just maybe this is luck, maybe not. The star we have is a good star. It's been pretty steady for a long time. It's been gradually getting brighter, but it's pretty slow and steady. It's a good star. We are not near hazards. There have not been gigantic explosions nearby. And this last one may be the most important about us. We have plate tectonics, which keeps recycling the rocks and the ocean and producing what might be the necessary spot. Now, there's a lovely book called The Vital Question that talks about the origin of life. Many people now have the opinion that these undersea hydrothermal vents, which only occur because of plate tectonics, are the chemical reactors. Because if you've seen the pictures of them, they're actually what forms is huge towers of tubes. And so each little tube is an intricate set of flow reactors. So if you were going to try to build an apparatus that would try trillions of different chemical reactions to see what would happen, you'd build one. So nature built them. So maybe that's where we came from. Who knows? So in astrobiology is now a new subject. When it was first mentioned to me, I thought, well, I know everything there is to know. There is no information. However, progress has been made. So Dan Golden in '99 said, well, NASA should be in this business. Finding life is really interesting. So we appointed Barry Blumberg to head our Astrobiology Institute. And he managed to get Congress to send some money, so we had vast amounts of ideas and proposals and activity that never had occurred before. So Dan was successful in starting a new subject, and I never knew that could happen. Anyway, there are at least 2 peer-reviewed journals, and there are lots of websites that collect the information, and it's a very lively topic. So not only do we have measurements of things that you think, well, maybe this could make life, but we also have theoretical simulations. You say, well, if I found a planet over there with life, what it would look like. So let's go think about this. So huge amount of progress is being made, and so the people can now tell us, please build a telescope like this. It would be the thing you need to know if you want to find out if planet Y over there is alive. So that's something I never expected. I never thought we'd get onto this, but here we are. So we have a lot of big questions, and some of them nobody could ever answer. Yeah, but number 1, carbon and water, the only combination? Well, let's go look at Titan. That would be a very different place. How about the nucleic acids? Are they the only way you can store information? I don't know. This is a physicist want to know, is there a reason for the right-handed molecules? Because if there is, we'd like to know. Maybe something about parity violation in neutrinos and things like that. So we haven't thought of a way among physicists why it should be so, but maybe. So this sort of the biggest question to me, though, is this a hard or easy problem? Is nature set up so that molecules spontaneously want to organize because it's exothermic? Or is it some special thing where the really random combination is very unusual? So I don't know. And we probably won't know for a long time. There are a lot of other things we won't know for a long time either. I used to say, well, maybe it would be easier except our ancestors ate all the evidence. So, so for instance, suppose there were 10 different kinds of life that occurred roughly at the same time. One of them won. You would never know that the other 9 had ever existed. So anyway, big questions for us all. For NASA, we say, well, what can we observe? So we can go visit, as I mentioned, we can go visit the other planets in the solar system. We can look for subsurface water. We can get pictures and try to interpret them. We can get samples. We already have some from Mars. And you might say, well, how did you get any of those? Well, things crash into Mars. Debris comes out. It goes orbiting around the solar system for hundreds of millions of years, and some of it falls on Earth. And how would you know that was Martian? We get the isotope analysis for the rare gases that are included in those rocks. And they match up with the signature that we measured on Mars and no place else. So, okay, that's Mars. We got some Martian rocks. And then a few years back, we had a great excitement because some people said, see these little tiny structures in the Martian rocks? That looks to us like it was alive. And we've been fighting over that ever since. And people have not agreed that that's alive or was alive. But we'll get some more. By the way, we get more every year because every year we go down to Antarctica and we harvest meteorites. They fall on the ice flows, the ice vaporizes and drops the rocks on the ground. So every summer we go down, pick up rocks, and some of them are from Mars. So it's not completely hopeless to learn these things, but you only get the random bits that happen to be part of a crash on Mars that way. So the other way, go visit and bring home pieces. So we've already brought 700 pounds of moon rocks. No sign of life in any of them yet. But we've sent out probes to comets and asteroids and started to bring home samples. So we'll find out. The other method, well, look at the chemistry of the atmospheres out there and compare them with what you think a system really could do. So we can see the molecules in the planetary atmospheres in the solar system, and eventually a little bit about the ones around other planets. We even can send a lab to Mars. Here's one. This is called the Curiosity. Landed or launched in 2011, and it has a huge variety of powerful instruments that have been miniaturized. So for instance, a mass spectrometer that you might occupy a whole laboratory is about as big as a bread box. And we built it over at Goddard Space Flight Center. So we found out a lot. We have not yet said we found signs that it was alive. We found that, for instance, the surface has perchlorates on it, which sounds unpleasant, but maybe underground there's something else. We're only scratching the surface at the moment. So anyway, we got one already. We'll talk a little bit about how far we could go beyond. Well, if you really want to go traveling, well, you can build a robot. And we've done a lot of that. They've been to all of the planets and a lot of minor planets, even dwarf planets. The computers are getting smarter, and they can beat us as everything that we can play on a game board already. But people, we need to be shielded by hardware. So engineers, their job is really important. We're not going to go very fast anywhere else. It's just too far. Right now, we just have chemical propulsion, and we've got electric propulsion that's a little better, but not enough better to get us there really fast yet. In the long-term future, if you can build a robot that can go really far, but it's going to have to be very patient. In the very short term, there's actually private money going into something called the Breakthrough Starshot, which is people have figured out that if you could focus enough laser energy on a small enough object, you could accelerate it to a speed of a quarter of the speed of light and get it out there towards Alpha Centauri, the nearest other star, and maybe even be able to talk to it. So they've put up $100 million of private money for this, so progress is being made. But I will not promise you that this could be done. It's only an idea. So if you want to go in person, we need your help. We got a lot of trouble going out into space. Zero gravity makes people sick, most of us. And so if you're going to go, you have to get proven out on the zero gravity airplane. Flies in a parabolic arc. We cannot avoid being radiation sick if we get cosmic ray damage, and I don't know if you all can help us with this. We need to take the magic pill that repairs the damage. We don't have it. We know that in zero gravity, we lose our bones and our muscles. And people have begun to think about this because we noticed people don't feel so good when they come back from the space station. And quite recently, we've noticed eye damage. It is guessed that it's because you no longer have the proper circulation of fluids in your body when there's no gravity to make things flow. The little bugs that infect us seem to change, and they get a little more aggressive. I don't know why. Plus, then there are hazards of being ourselves. So we try locking up people in a simulated mission, and some of them take it, and some of them get a little crazy. So going in person is hazardous, but we've got a research program that NASA runs to try to figure this all out. And so many topics. If we want to be self-sufficient, we're going to have to work pretty hard at it. We can probably recover the water and the oxygen and get some of those from local sources. We can make heat and power with solar cells and batteries or nuclear reactors. The hard problem is probably the farming. If you say, I'm going to go live on Mars for a long time, but don't send any food, you're going to master farming, and there's nothing easy about that. What's been tried is always unstable. One or other system, a species that you put into your sealed box takes over and becomes different. So We don't know how to do that yet. And so that's a good problem. People here on Earth actually might like to be self-sufficient. But at the moment, it's just easier to send an awful lot of food. So if you're going to live on Mars for 50 years, take 50 years of food with you. So we've got programs. In fact, one of the most interesting ones is we've got twin astronauts. So there are 10 major studies that are in progress, and here's just the first one on the list. We're comparing our two astronauts, and they're different. So we've learned something. Our astronauts are identical twins, which helps a lot. So then we come to the end. What's the billion-year challenge? How are we going to manage everything else for a long time? And I'm not going to answer that one. We have about 1 billion years, by the way, before the sun gets too bright for us, and then we have to move. That's why it's 1 billion years here. And then about 3 or 4 billion years, we have this. This is when our nearest other galaxy, that beautiful Andromeda Nebula, comes in our direction. And our two galaxies, the Milky Way and Andromeda, will merge together into a new galaxy of a completely different shape. And whether the solar system is in the middle or on the outside, we have no idea. But it'll be an exciting time to be an astronomer. So I think I'll wrap up here. We have a few minutes for questions, and then Dr. Lippincott will speak. Okay, questions?
Please use the microphone.
Okay, use the microphone, particularly so the people on the internet can see it.
You showed the animation of the Webb unfolding itself. How long does that take?
Oh, the unfolding of the Webb telescope, about 2 weeks is allowed for it. We're not in a hurry. The robot is not bored. We have to make sure that every step goes correctly before we go on to the next step. Yeah. So it's not like landing on Mars, which we had 7 minutes and with no control from here.
So, John, is the universe rotating?
Is the universe rotating? Probably not. We have been looking to see if there's any sign, like, is there an axis? Or is there an equator? And so far, no sign of anything.
But if it were, could we move backwards in time?
I don't know. That's actually the universal answer to a lot of things, is I don't know.
So you talked about how lucky we are to be here, and some take this to an even further step of how lucky we are that we have a universe that's actually capable of complexity. This is this argument about fine-tuning, that there are constants like the gravitational constant or the strong and weak nuclear forces, that you cannot derive the value that they have. They just are what they are. And if you tweak them just a little bit, making them stronger or weaker, the whole thing doesn't work anymore. You don't have a big bang that leads to anything interesting. And it basically becomes a sterile universe that either goes on forever or lasts a very short period of time. And so people are then kind of feeling like there must be some other explanation. Maybe we have to talk about multiverses. You're a physicist. Help us sort through, is that likely to lead to any concrete conclusions about how to resolve what otherwise is an incredibly puzzling situation that we seem to have been so remarkably fortunate to have all these constants have exactly the value they have to have for anything like us to be here?
I have no idea what the right answer is to your question. That's a really hard question. Because if you really wanted to know, you'd have to know if those other universes do exist.
Exactly.
And we have not thought of any way to find out. Not yet. The mathematicians have ways to simulate and say, well, if my equation is right, then there should be more universes. But of course, we have more ideas than we have measurements. So the statistical certainty about this, no measurements and infinite number of theories, is low. So ask again in another century, we might have a better answer.
I have a quick question. When do you think, what is your perception of where the gravity actually occurred, the way we understand it? It is such a nebulous beginning.
About gravity itself. Yeah, this is actually a subject of hot pursuit by physicists at the moment, so I can't answer your question either. Well, the essence of it is, well, is gravity just something that we have to accept because that's how it is, or is it produced by something else? So Einstein made this amazing breakthrough where he said, well, gravity can be represented as something that curves space and time. And that accounts for a lot of things, but it's still very startling. And so some people say, well, gravity is so weak, maybe it's just some other force leaking through. So there's an idea that there's a universe with another dimension and shapes of things in these other dimensions where just a little bit is leaking through from the higher dimension. And there are other stories that say, well, it's a thermodynamic force like osmosis, which osmosis is real, but we understand it in terms of other forces. So as a kind of statistical force. So there are ways to think about this, which we will come back to Stephen Hawking 2.0 maybe, and we may have a better answer for you in another few years, but even Stephen keeps changing his opinion about some of these things. So this is a hard problem. You ask hard questions.
So the Hubble project was under a lot of pressure from Congress and from the public to produce useful results. When I was a kid, that was a really interesting thing, was the optics didn't work out and they had to fix that, and that was a huge snafu. How much pressure is on the Webb telescope in terms of producing results? Is the
no
environment
pressure
the
at all.
same?
No, clearly we've invested a fortune in this thing. It costs somewhat more than the Hubble to build. It's much more powerful. So if it works at all, it should be immediately produce astonishing results. But our hard problem is you can't go fix it if it's not working. So that's our big challenge. Almost all our projects work the first time, but there's always a chance. So that's what we're doing now, actually, is making sure that all the rehearsals and all the tests go according to plan. And if they don't, we take care of everything because we don't get another chance. So assuming that it works, we will expect to surprise you with wonderful pictures immediately. By the way, there's a story that should be told about the Hubble and why it was out of focus. They built, the team that built the mirror measured it, and they said it's okay. And we did not have a separate independent measurement of that mirror. So like the carpenter says, measure twice, cut once. They did have two tests, but they decided the wrong one was the correct one. So so the most general answer is, if you really want your answer to be trustworthy, two teams with two separate sets of measuring equipment, so you can reduce the chance of human error getting through both. So if we'd done that, we would have known. But pressures were high at the time, and the Hubble mirror was built in a classified optics facility, so NASA engineers were not really welcome. So we couldn't say, I'm going to look through the eyepiece with you to see what you see. And so errors crept in, and we didn't measure twice. So anyway, remember, if your answer really matters, measure twice.
So could you possibly comment on dark matter, dark energy, the black hole, that of which we cannot see?
Yeah, I can say a little bit about it.
Thank you.
Astronomers are sure that they exist. What is dark matter? Dark matter is something that has gravity and is much more abundant in terms of mass than we are. And we wouldn't be here without it, according to the stories we measure. So it's really important to us, even though it's completely transparent. It was not predicted by any particle physics theory that we should believe. So it's a surprise. The second big surprise is called the dark energy, which is causing, it's a name we give to whatever is making the universe go faster and faster and faster every year. And it's a complete mystery. It's allowed in Einstein's equations. We didn't think we'd see it. Astronomers were prejudiced against it. So when it turned up, the young people that found it had to really struggle to prove they were right. And then there's the black holes. We're darn sure of black holes because we see stuff falling in. And we also see stuff orbiting around them, and we know there's no other explanation that we've found. So black holes you can be sure of. Dark matter and dark energy, much more mysterious. One more question, then we'll go on to our next speaker.
Yes.
So basically, probably naive question for a biologist, but you position everything we know is by telescope. We position close to Earth or on Earth or something that is not that far. But what will happen if you want to look for the signature of life? If you position a telescope which is as far as you can go with science, and then try to look on the signature of Earth, and then see if really the mathematics we use that we think can calculate the life on Earth can be used for finding. Yeah.
Okay. Well, actually, it was a good idea, and it's been done. What we did, or I should say other people did, was they said, well, imagine you were a telescope looking at Earth from far away. What would you see? So what we've got is the moon as a reflector from Earth. So we look at the light that comes back to the telescope from the moon that went from Earth to the moon to back. So now we can say, what would Earth actually look like, and how would you figure out, if you didn't know what it was, would you know? And so we've done that one, and we can use that as a model for what Earth would look like if it were way out there. So it's not easy to tell, but it's better than nothing. Okay, thank you.
Okay, wow. To follow a talk like that is quite a challenge and very exciting. So we've just heard about imaging the cosmos, which has been a long-standing curiosity for all of us. And really our ability to make a lot of the sort of comments, the ability to understand the cosmos in the way that I think you've just heard was very much dependent on imaging technology, which way back in the 1600s was something as simple as Galileo's refracting telescope. And now in the 21st century, we have these large 100-millimeter array reflecting telescopes like this one here at the University of Texas in Austin. What I want to focus on today is turning our optical instruments inwards and what we've learned as a consequence. What's interesting is that paralleling the work looking outward at the cosmos, starting in 1600s, was work looking inwards by van Leeuwenhoek with the first microscope. And the developments of the inward-looking microscopes have evolved throughout this 400-span period, analogously to the way that the telescopes have evolved, which is very exciting. And so I just have a picture here of the lattice light sheet microscope, which I think is probably one of the most complex of the existing light microscopes that we have today. And it's a microscope I'll tell you a little bit more about and show you some of the things that it can do. But there's a uniqueness to imaging at inwards. And that is, A, you're looking at life, or you can look at life. B, you're studying events up close. And what that means is that you can follow rapid changes. One of the challenges if you're looking outwards is things are so far away, they're not happening. It's very difficult to see things happen quickly. When you image life and things at the small level, you can follow movement very quickly. And importantly, you can manipulate and do experiments here and now. You can control what you're looking at. And so that's what's made the uniqueness of imaging life so special. But there are many similar challenges in imaging life, as we know it, to those that have been faced by astronomy. And the development of microscopy has benefited from innovations in telescopes, which I will show later on. So there's a parallel in these two imaging approaches that on the one hand allow us to understand how the universe as a whole is functioning, and on the other hand is allowing us to look at what we feel is dear to us, and that is our own inner workings as living organisms. Now, one of the first things that was really discovered with microscopes was that all life is comprised of cells. One of the first things that van Leeuwenhoek and his colleagues were able to see when they looked in a droplet of pond water are small little organisms like this paramecium, which are about 150 microns in length, and they move all over the place through the activity of cilia. But what Van Leeuwenhoek and his followers also found is that you can take a toothpick and just pry off a part of your cheek and put it under these simple microscopes. And you can see, again, the material that's making up tissues is also comprised of cells. So that was, again, reinforcing the concept that life is really, can be described in terms of very simple parts. But perhaps the biggest breakthrough in this concept came from Ramon Cajal, who was looking at brain tissue. And for many years, there was a huge controversy because when you examine brain tissue, what you see are very complex structures that for many years people had really felt were just a single elaborate sort of living system and not necessarily comprised of distinct cellular units. And Ramon was able to show, using his elegant microscopy approaches, as well as introducing staining strategies, that the brain is made up of individual cells that we now know as neurons and glia and astrocytes, et cetera. Now, as we move forward, as the field moved forward, really one of the great breakthroughs in microscopy was the recognition that cells are actually subcompartmentalized. And that subcompartmentalization, although it was first hinted at with the simple microscopes, became much more apparent as these microscopes became more advanced, compound microscopes on the one hand, but on the other hand, the ability to stain cells, to highlight with dyes, initially with antibodies tagged with dyes, and then finally with fluorescent proteins that are introduced into these systems to then identify particular compartments of the cell. Now, once people started realizing that cells are subcompartmentalized, they wanted to know what are these compartments, and a huge field of cell biology emerged to describe the activities of these different organelles: mitochondria, nucleus, endosomes, lysosomes. But very quickly, it was realized that many of these structures are below the limit of resolution if you use a light microscope. And that resolution, if you're imaging objects, looking at using green light as your imaging venue, is about 250 nanometers in XY and about 500 nanometers in Z. So any objects that are closer than those dimensions will appear as one merged structure. And we have no ability to distinguish between them. And that's called the Abbe diffraction limit. Now, because many of the details of cells are actually occurring below this diffraction limit, there was a huge challenge to try to understand how imagers could break this diffraction limit. And this led to the field of super resolution imaging. Super resolution imaging can push you from this 200 nanometer barrier in XY resolution to down to 10 nanometers or below in some cases. Now, what are these super resolution imaging techniques? There are several of them, and I'm highlighting two of the main varieties that emerged in roughly the same time period, which is really interesting. Science progresses in a way where frequently you have questions that are identified, and then researchers in different fields sort of come together. They cross-fertilize concepts that lead to solutions. And so one of these super resolution imaging approaches is based on essentially sculpting the light path using either STED or structural illumination microscopy to be able to focus smaller than the diffraction limit. Another approach is based on single molecule-based imaging, where instead of sculpting the light path, what you're doing is you're modifying the system so that you can identify light coming off from individual objects, in this case molecules. Now, one of these techniques that I want to talk a little bit more about, PALM, was, as was mentioned earlier, was developed here at NIH. It was a very exciting time. We hosted Eric Betzig. Basically, he realized that a single GFP or a single fluorophore is a point source of light. In fact, many people during this period recognized that single fluorophores, much like stars, starlight, are point sources of light. And if you look at these point sources of light through an objective, a lens, that light's going to be diffracted. But in the case of the lenses that we use on our common microscopes, the diffraction has a roughly Gaussian profile, so that you can fit the centroid of that Gaussian profile to determine pretty precisely where a molecule, in this case a green fluorescent protein, which is about 2.5 nanometers in diameter, where it's sitting in that isolated spot. So for many years, people recognized this, but they ran into the problem of trying to use this as a way to image dense populations of molecules. And the reason is because the point spread functions of many molecules, if you're imaging them simultaneously, will overlap, and you'll just get a blurred signal. So what Eric Betzig realized is that using photoactivatable fluorescent proteins, like the one that we developed at George Patterson in my lab developed, the photoactivatable GFP, you could switch on individual fluorophores, point sources of light, and each time they're switched on, you can fit the centroid of that spot. And if you do this over and over again on a specimen that's fixed and not moving, what you can do is build up all of the distributions of these proteins. And if you sum up those, the positions of those proteins, you can get a super resolution image. And that's what's shown here. This is an aggregate of 50 nanometer polystyrene beads. They're all coated with a photoactivatable fluorescent protein. If you were just imaging them with a conventional confocal microscope, this is what you'd see. All of these beads their fluorescence would overlap because the beads are closer than the diffraction limit of light. But once you isolate each one of these beads using photoactivation to sequentially switch on individual fluorophores, you can map the centroid of the fluorophores and get a super resolution image. And so this technology has given rise to a whole plethora of similar strategies using other fluorescent probes to essentially create super resolution images using pointillism. You can get much lower than the diffraction of image of light by using this approach. Now, as great as this breakthrough was, we as imagers of life, if you will, used many tips from astronomers, or have used many tips from astronomers in terms of further implementing this way of imaging. First, and I've just listed three examples here. Astronomers are widely known to be able to, map out the distribution of stars using and looking at relationships in terms of these point localizations of stars using fitting and paracorrelation analysis. And we can use exactly those algorithms and apply them to our palm and point localization images to understand how individual molecules that we're visualizing are associated with each other and how we can separate overlapping point spread functions. Another approach is interferometry. Again, you heard a little bit in Dr. Mather's talk about interferometry, how important it's been in astronomy. We can also use interferometry. Down here is an example where you can combine interferometry with palm to precisely localize in Z where a particular fluorescent protein is emitting its fluorescence. And finally, and this is most recently, adaptive optics is coming into play. And basically, it uses deformable mirrors to compensate for wavefront distortions, much like the way astronomers are able to use the deformable mirrors to compensate for the light coming in from stars moving through our atmosphere, which distorts what the image is. So all of these tricks, if you will, that astronomers have used to better visualize the skies, we as biologists can use with these super resolution approaches. And as a consequence, many different areas have been opened up because of our ability to image at these much finer levels. So I've just showed you some examples here. To the left is an eye palm image looking at the endoplasmic reticulum, where we're imaging the distribution of individual molecules. To the middle top is just tracks using single particle tracking of an individual molecule on the surface of the cell. To the bottom left is an eye palm image where we're reconstructing the distribution of different molecules in an HIV virus to try to understand, well, to better understand how these different molecules are positioned as well as potentially functioning to create this infectious agent. This is an example of a paracorrelation analysis where we have all of these individual point localizations of receptors on the cell surface. And by using a paracorrelation analysis, we can determine how big clusters of receptors are on the cell surface, the diameter, the relative abundance of these proteins in these clusters, et cetera. And from that, get insight into how receptors on the surface of the cell are playing a coordinated role in terms of receiving ligands from their medium and propagating a signal inside of the cell. And then here's just finally an image of the actin cytoskeleton, which you can also obtain using these super resolution imaging approaches. So one of the big challenges that we've faced as a field is to localize proteins which are coded for by DNA and essentially represent the basic building elements of life, because they are they drive not only the structure inside cells but also the function and catalysis of biochemical activity. So how are these proteins localized inside cells, and how are they associated with particular organelles? And this has been very hard because although we can do this using diffraction limited images with where we're looking sort of in a cell that's flat in one dimension, it's been very hard to understand how organelles and proteins organize themselves in 3 dimensions throughout the entire cell. And this is where these new microscopes, like the lattice light sheet microscope that I mentioned at the beginning, are playing an important role. The lattice light sheet is not just a beam of light that's being passed through your specimen. It's a sheet of light. And that sheet of light, the value of passing a sheet of light through a cell is that you can essentially pass it through very, very quickly. And at every plane, you can interrogate information. You can get information from every plane to create a 3-dimensional vision of that cell. Now, I want to show you how you can couple the lattice light sheet microscope with these point localization super resolution imaging approaches to get very high resolution in a whole cell. So basically what we're going to be doing is we're going to express a probe that binds to membranes in cells non-specifically. It's just a global membrane marker, and we're going to use the lattice light sheet to interrogate every plane at 150 nanometer slices and look at using super resolution imaging how each of these how the probe distributes on all of the membranes within the cell. Now we're just moving up and down this fixed cell to show you each of the planes. I'm going to zoom in on one plane that we've imaged, and what you can see is all of the organelles in that plane identified using this point localization approach. So basically, we're using a Boddippy tetramethyl ester dye that binds and dissociates from membranes very quickly. Whenever it's bound to a membrane, it's a point localization source of light. We can fit it at very high resolution, and then we keep summing up the positions of all of the dyes association with these membranes, and we can get millions and millions of molecules that, when they sum up, give spectacular images of the interior membrane design organelle structure of the cell. And just as an example, I've zoomed up in one region of this cell, which comprises the endoplasmic reticulum. So here you can see these tubes that extend out in this exploratory way. The endoplasmic reticulum is a wire meshwork of membranes throughout the cell. And this is an area where that meshwork gets super tight, very tightly clustered. That's something that hadn't been seen before because we didn't have full 3D reconstructions at this resolution of a cell, nor spatial, distinct XY spatial resolution. Now, because we have the ability to look at images like this, where we have the whole cell and all of its organelles displayed, we can superimpose or correlate the distribution of particular molecules on top of those images. And here's where we've superimposed a molecule, Sec61 beta, that has been tagged with a fluorescent probe onto the backdrop of those membranes to allow us to look at how this particular protein distributes. And it's very much localized throughout the entire endoplasmic reticulum. So I've just showed you how, with improved imaging technologies, we've begun to really been able to chip away at understanding how proteins are distributed in a 3D ultrastructural context. I want to now move to looking at organelle dynamics. Everything I've told you up to now are cells that have been fixed. These super resolution imaging approaches require the cell to be static in order to build the images. But we know cells are not static. They're highly dynamic. And new imaging approaches are allowing us to begin to really understand these dynamics. But one of the challenges has been using fluorescent probes is that because fluorescent probes can overlap in their emission spectra, it's very difficult to image more than 1 or 2 or 3 of these fluorescent probes simultaneously because of their emission overlap. And that's illustrated here, where we've tagged 6 different organelles, lysosomes at the top, then mitochondria, ER, peroxisomes, Golgi, and lipid droplets, with different colors, different fluorescent probes that exhibit different emission spectra. Hence, they appear as different colors when you image them under the microscope. Now, what you can see is we move through the emission wavelength of our microscope. There is no wavelength where one organelle can be seen without also seeing another organelle. And that makes it impossible to be able to visualize these different organelles separately from each other. So we don't understand, we haven't been able to look at how organelles are all behaving simultaneously. So how do we get around this? Well, one strategy is to employ multispectral unmixing approaches. And again, this has been around for a while. Many different fields have recognized that if you have known spectra of different fluorophores, you can unmix an unknown spectra simply by using, essentially use various algorithms that will allow you to unmix. Use a matrix inverse operation, and you can essentially say, I see this. What combination of these fluorophores gives rise to that spectrum? And once you've done that, you know you can call a particular pixel as lysosome, Golgi, ER, based on what it has been tagged to. So we've done this using the lattice light sheet microscope to try to look at how all of these organelles are behaving dynamically. And basically, what we've done is put 6 different laser lines to excite the 6 different organelles that we've tagged with different fluorophores. And we can modulate which laser is turned on with this adaptive optics system. And from that, turn on each of the different fluorophores and feed that information into our camera, and then ultimately use linear unmixing algorithms to separate the overlapping spectra. And when we do that, we can now see all 6 of these organelles simultaneously in the same cell with no overlap. These are the different organelles as seen separately. In a second, I'm going to show you how they look in one cell. But I just want to draw your attention. We have peroxisomes, mitochondria, ER, Golgi, lysosomes, and lipid droplet. And if we look at how they fit into a single cell, you can see from this type of movie how they're very quickly moving around. They're moving along microtubules. They're being propelled by actin cytoskeleton. It's a very dynamic system. Now, one of the things that we could do from this type of analysis, because we have 3D information on all of these organelles, is we can measure the number of these organelles per cell. We can look at their mean volume. We can look at their speed. I'll just draw your attention to these 3 volume measurements. The ER is by far the largest organelle in the cell, with the Golgi, mitochondria essentially 8 to 9 times smaller, and the Golgi is about 30 times smaller in terms of the volume that it occupies. Now, one of the things that we realized when we did this analysis, which required segmenting these different organelles from these 3D image stacks, is that many of these organelles are actually talking to each other. They're making contacts. And so this is a matrix diagram where we're matching the extent to which different organelles are overlapping in their pixel distribution, suggestive of the organelle communicating with each other. Now, what do organelles do if they contact or communicate with each other? Well, they can essentially share lipids. You can have lipid move from one organelle to another. Calcium can move at these contact sites. Reactive oxygen species can be transferred through these contact sites. So we are now just beginning to realize as a field that there is a whole level of communication going on between or among these organelles that we had not appreciated, that is arising because of the way these organelles are contacting each other. Now, I want to just sort of emphasize this further by showing you the contacts between mitochondria and ER. So to the left is a segmented mitochondria from these lattice light sheet movies. And what we've done is then asked, on that segmented mitochondria, what portion of that mitochondria is the ER touching? And that's what we see. So it's a huge part of the mitochondria that's in very tight communication with the endoplasmic reticulum. Now, I mentioned the ER is the largest, occupies the largest surface area of the cell. In fact, if you exclude the nucleus, it occupies about 25% of the cell volume. Now, what is even more amazing is that if we track the space that the ER moves through over a 15-minute period, what we find, and we can do this using the lattice light sheet, we're just essentially mapping out the position of the ER over 15 minutes. What we find is that that organelle explores at least 97% of all of the space in that cytoplasmic volume. So this is telling us or reinforcing this concept that the ER is a sensory, it's sensing the cytoplasmic milieu. It's essentially it's a master organelle, if you will, that essentially keeping tabs on what's happening throughout the cell. Okay, now in the final part of my talk, I want to move to this temporal feature of imaging at the life scale, if you will. Microscopes can image fast. Cameras have improved their speed dramatically over the last 10 years so that we can look now at how these organelles are moving on the scale of milliseconds. And we can also look at how their protein constituents are moving. So one approach that we've employed, and this is in collaboration with Eric Betzig's group, is to employ a microscope that does total internal reflection microscopy so that you can focus in on just one small part of a cell that is in this total internal reflection zone of a microscope that is laser that's coming in at this angle that gives an evanescence waves that excites only a small part of your field of view. So you got one plane that you can image super fast. And we can combine it with structural illumination microscopy, which gives you a twofold increase in resolution. And so together you can get about an 84 nanometer lateral resolution and image at sub-second speeds over hundreds of time points. And so we've been able to look at this. These are three people who've played a huge role in my lab. Initially, Johnny Nixon Abel was in Craig Blackstone's lab, and he came over to our lab and said, I want to look at the ER. And Chris actually then came to me and said, what do you think of this image? And I said, it's crap, because they were just looking using a confocal microscope. And I said, okay, let's see if we can really look at the ER. Let's get over and use this turf sim system and look at how the ER is at these fast speeds at twofold increased resolution. And this is what we see. 25 milliseconds per frame. This system is made up of tubules, three-way junctions, and the system is constantly sort of oscillating and rearranging. One of the things that was surprising is that the tubes were oscillating at faster than the shutter speed of most conventional microscopes. That oscillation, we found, is not due to just thermal motion or Brownian motion. It's due to ATP and GTP-dependent processes. And we think that one of those processes may be related to the actin cytoskeleton, the other may be related to protein translocation. What this motion does is allow three-way junctions to collapse and pull apart. This is going to be in collaboration with the ability of these tubes to anchor themselves on microtubules, to be pulled out on microtubules. But we also think the rest of the cytoplasm is undergoing a type of motion that drives this type of oscillations that give this kind of dynamism to the ER that ultimately ends up in the ER being able to explore the entire cytoplasm in such an efficient way. Now, one of the things that we found is that we're looking at this ER just using total internal reflection microscopy. There were areas of the ER that looked like they were smooth sheets. And this had been reported and studied by many people in the lab, not many people in the field, and they were describing these structures as sheets. And what we found when we switched on our structural illumination microscope was that these weren't sheets at all. And in fact, if we started imaging them at high speeds, what we found was rather than being sheets, these structures were tight clusters of three-way junctions that were being slid together as a result of this dynamic motion of the ER. And we think that it's this kind of ability of the ER to really drive itself from loose sort of networks to tight clusters like this is going to be important for how the ER is able to sort of spread itself out in a cell that's migrating and moving in different places. Now, one of the things that we know that proteins move within membranes, and they move within the ER. The ER is full of many different types of proteins. And we were interested in trying to see if we could use these single molecule super resolution approaches to track how individual proteins move in this diverse organelle. So what you're looking at here in the backdrop is an ER marker where we can see the profile of the ER. And then we're using a halo tag that is bound to a Rab18 protein that localizes to the ER membrane. And then we come in with a photoactivatable dye to allow us to switch on these molecules and identify individual proteins to track them. So here we have another example where we're looking in real time now at the motion of a calreticulin protein in the ER. So this is tracking an ER luminal protein that diffuses very, very fast. It's diffusing, we believe it's diffusing, and right now we're also trying to determine whether these luminal proteins undergo flow within this luminal system. Right now, we haven't been able to nail it, but we're looking at different types of luminal probes to determine if it's just diffusion or is there a flow, and is there what drives changes in the motion of these proteins. Now, one of the things that you can see from here is that this system is fully connected. The ER is a continuous organelle, expands from the nuclear envelope all the way out to the periphery of the cell, but it's continuous because we see these particles move throughout it. And here is just this movie slowed down a little bit so that you can see how these proteins are behaving. Now here we're looking at a membrane protein. This is Sec61 beta. We've color-coded the speeds of these different fluorophores. Fast is red-colored, and blue is more slow-colored. Now, because we can determine the instantaneous velocity or the diffusion coefficient of these proteins, we can begin to look at proteins that we would suspect might have changes in their motion as a consequence of interacting with other elements. And one of these proteins is VAP-B, which is a tethering protein that tethers the ER to the mitochondria. So in this movie here, what we've done is we have three colors that we're introducing. We have an ER that you can see in white, so we know where the ER network is. We have in red a mitochondria marker, and then we have our protein of interest, VAP-B, that we're tracking. And we color code our tracks based on whether that VAP-B is moving fast or moving slow. And when it moves slow, we look at where it is, and sure enough, when these molecules are moving across the ER that's in close vicinity to the mitochondria, we can see that the VAP significantly slows down. Now, I want to end now because I could tell you a lot more things in the field. This is a really amazing time to be a biologist and to use imaging. But I want to try to connect this to this bigger picture that we've talked about today. It may seem like these two areas just cannot come together, but I've showed you how we share common instrumentation. We share common sort of intellectual tools at trying to understand the objects that we're looking at. I mean, it's amazing that you put a fluorophore on a single protein and you can treat it very much like starlights, individual stars, and use the same types of algorithms for trying to understand the distribution and behavior of these systems. But I want to also say that I think it's going to be absolutely keeping the communication between these two fields is absolutely critical. I've run into many astronomers who've moved into the biology field, and they're definitely into the imaging field, and they're always they always come up with very, very creative ideas for how to analyze the light microscopy-based images that we're pulling up. But I think that closer collaboration between these fields is also going to be absolutely amazing to begin addressing some of the really amazing questions that you raised, which is the origin of life and where we're headed. So with that, I want to end by thanking people that have been involved in this work in my lab, past and present, collaboration with Craig Blackstone, and key people at Janelia who've been vital to this work. Thank you.
So hypothetically speaking, when we find life on other planets, which scope do you think is most likely to become the mini version that they're going to stick on the rover?
That's a good one. We may be back at Van Leeuwenhoek, which is a really small little thing. I don't think it's going to be the lattice light sheet. Gokul, are you still here? He's one of the big lattice light sheet sort of gurus that's been working on it. I don't think it would fit on any of those rocket ships. But that's a very good point. I think NASA and NIH are going to have to start talking if NASA is really making it to Mars, because if you really want to look at what's going on there, you got to start thinking from the perspective of what these imaging approaches have. I mean, I think right now the big problem has been, we really haven't done much imaging at Mars. It's all been biochemistry. The closest the imaging has come to is some of these asteroids that came out of Antarctica, and that actually went into a huge controversy because pretty quickly the biologists realized that these small structures that they thought might be life on these asteroids were way too small to be a cell. You couldn't have enough key molecules to drive the engine of life based on the size of those little, I can't remember what they're called, the particular formations that were on that asteroid that they thought was potentially a precursor, even a form of life. So very exciting in terms of crosstalk between these different fields. So Wynn, I want to thank you so much for bringing us together in this way, because it's very exciting. I like thinking about this, and you know, I'm a neophyte in probably both fields at some level.
So Jennifer, it's so beautiful to see the kinds of images you can obtain. The other area, of course, in cell biology that everybody's really excited about as far as imaging is taking cryo-EM and turning it into cryo-EM tomography, which maybe can start to look also at cells at a level of resolution, maybe
Absolutely.
even slightly further down. People must be thinking about how to combine those kinds of images so that you can learn from both of them.
Absolutely.
Is there a good crosstalk there between those,
Oh, yes.
those technologies?
Actually, I didn't have time today. I chose not to go into electron microscopy. Sorry, John. But this is the hot area. Basically, we have not only electron tomography, but also focused ion beam milling, where you can mill 4 nanometers, image using scanning EM, and you can scan through a whole brain or a whole tissue. And one of the things that we're trying to do at Janelia with the colleagues, in particular Harold Hess, has developed a focused ion beam scanning EM that is stable for months, if not years, in terms of just slicing and slicing and slicing at 4 nanometers. And then you segment each of those 4 nanometer slices, or before they're sliced, you segment, slice it off, go to the next one down, and you can get incredible resolution. You get 4 nanometer voxels that you can reconstruct into pretty spectacular images of the whole cell. So what we're interested in is trying to do this for a whole cell and segment everything that we can get our hands on. So that's sort of the big, it's sort of almost like a, well, I don't want to say it's a moonshot, but it will take quite a bit of time, because right now we do not have the software to segment automatically. So we're right now segmenting by hand and using that as ground truth for computational specialists who will use algorithms to try to reconstruct automatically.
Jennifer,
Yeah.
what do you think of the prospects of linking intravital microscopy at the levels that you were speaking of here?
Yeah, I think it's absolutely amazing. It's another frontier is intravital imaging. One of the challenges of that is aberration, tissue aberration, because tissue is dense. It's, light can't pass through it very easily. But the adaptive optics innovations that you can take out of astronomy are playing important roles in really making our ability to do intravital imaging using some of these amazing microscopes like the lattice light sheet possible. And in fact, GoCool just published a adaptive optics lattice light sheet implementation in bioRxives just a couple weeks ago. And if any of you guys are interested, you should definitely go look at this bioRxives paper. It's mind-blowing. And there was intravital imaging in that paper.
Jennifer, many of the things that we are using for all the application you showed is really using photons as light.
Yes.
How about using other sources of light that is not necessarily photons?
Oh, yeah. So, I mean, electron microscopy, I just chose to focus on light, but, electron microscopy is hugely important. X-ray microscopy is also very powerful. And it won't take you to the level that electron microscopy will, but X-ray tomography has been very successful. We've been using X-ray tomography to look at yeast in 3D. It's just perfect in terms of the right size and speed.
Thank you. Have you had a chance to apply any of these technologies to patients who have defects of some of these organelles?
Yeah. So basically, the work that we did with the ER was done in collaboration with Craig Blackstone, because he's somebody who works on spastic paraplegia diseases, that the genes that essentially are mutated that give rise to these disorders are almost uniformly associated with proteins that shape the endoplasmic reticulum. And so we've been imaging cells from patients with these mutations and also introducing those mutations into cells that we're imaging, the proteins that we're interested in that are in the ER, in order to see how they're impacting the structure of the ER. And we're also doing that in collaboration with Michael Ward here at NIH, who's working on progranulin. And mutations in progranulin underlie ALS and frontal temporal dementia. And we have some very interesting results related to that. Again, imaging progranulin and what, when it's mutated, what the impact of that is on organelles like the lysosome or the process of autophagy.
Yeah. So my question is about what makes stuff move up and down. What are the motors in there that move the stuff around inside the cell? Should I picture a little ladder with cog railway, or what do I picture?
There are 3 types of structures that objects can move on, organelles can move on. One is microtubules, and that's almost like a railway. It's made up of tubulin subunits, and there are motor proteins kinesin and dynein that walk on that railway. And they are tethered to vesicles or other membrane-bound organelles. And that's how you move up and down. But another cytoskeletal structure that works in a slightly different way is intermediate filaments. And they actually structure the position of the nucleus and potentially control how things are structured inside that nucleus. And then the third is the actin cytoskeleton, which is playing a very important role in structuring the plasma membrane and events happening at the plasma membrane. Many of the people here could correct me on some of this, because this is the world, this audience is actually, many of the experts in these areas are right here. It's amazing.
Well, we have to thank Jennifer, and they're going to stay here for a few minutes, so if you have informal questions, please come and ask her as well, and Dr. Miller will be here. Thank you.